First of all, thanks. I would like to thank the organizers and Jim, particularly, for the invitation. I'm very glad to be here to share with you my experience and some of my ideas, my group ideas in lifelike materials, in smart material, this kind of thing. So a brief introduction to myself. My name is Hao Zeng, and I did my PhD in Florence about 7 years ago. So I had a very, very great time in Italy, and I also attend some summer school, maybe like you are doing there now. So at that time, what I believe it was the alcohol and beach and good food and are the best way to do science. And then I moved to Finland after my graduation. And basically, there's nothing in Finland. The weather is very bad and no good food. So we can only do the sauna to get them stimuli. Yep. Today, I'm going to talk about one strange material. Those are the movies about this material. Some can bend. This is underwater. Some is oscillate. Some is like the human iris. And these three guys, they are in microscopic scale, and this size is about 60 micrometer. So something big, something small. So all of them, you can call them liquid crystal elastomers. The chemists, they have different kinds of name for it. Liquid crystal polymer, liquid crystalline network, cross-linking network, this kind of thing. But since I'm a physicist, I don't need to worry about the name, so I just call all of them liquid crystal elastomers. So today, in this talk, is about 25 minutes. So the learning objective is I will tell you something about this material. And second is I will tell you how to make a self-oscillator. And the third is a locomotion and how to make it fly. Before you may hear about the story about walking or swimming. So today I will show you the flying. Let's see if I can convince you. Yeah, my another belief is study only for your interest. If you are not interested, you can just go to sleep, and I don't mind. This is a slide I would like to show in most of my talk. This is the example. It's the first result I obtained in my research. It was exactly 10 years ago when I was in Florence doing my PhD in Professor Dietrich Wiersmer's group. And we obtained the first result about liquid crystal elastomer. So here you can see some very ugly thing deforming under the focus spot. And my supervisor, Dietrich, is a very great scientist. And I believe today I have a lot of good ideas and I can do good science. I think it's because of him. He changed my way of thinking about the science. So after this ugly result, so I have to explain what exactly happening inside this kind of material, why they can deform. So the principle is very simple. It's liquid crystal. So I guess this morning other professor like Professor Asando, they have explained you the behavior, the basic behavior of liquid crystal. So I think everyone knows it. So liquid crystal has the order. It has liquid crystalline phase. But if you heat up the system, heat up the structure, it becomes disorder. So everything will mess up. But what we are doing in this kind of liquid crystal molecule is we put some chemical bond, put some acrylic bond on each molecule. So we can use the polarization process to link them together. So each molecule, they will connect to each other. So the liquid crystal is not liquid anymore, it's a solid. Since it is a solid, it has a shape. But if you can heat up the sample, it still maintain the liquid crystal phase. So you can go for phase transition and become disorder. But remember that the liquid crystal molecule, they are quite long. They are packing one by one to each other. If you go to disorder, the distance of the molecule, the spacing will change. So the solid material will just deform, will contract along the alignment, the orientation direction, and expand in other two directions. And in this way, we obtain the deformation, and we call this material liquid crystal polymer or elastomer. And because it has the direction to contract and expand, if you make a fiber, and you can work as an artificial muscle to keep this kind of, if you heat up, you shine the light and heat up, you contract. If you switch off the light, you relax. It's like a muscle. But very often in literature, what you see is this kind of bending or bending into different direction, this kind of thing. So you may ask, oh, it's nothing to do with contraction or expansion. It's bending. It's a different story. Well, it's not, because the scientists know how to do the trick. The trick is, for macroscopic scale, if your sample is like a piece of paper, if you look at my face, it's a piece of paper, it's super easy to bend, very easy to bend. So liquid crystal, you can control the liquid crystal orientation, the alignment, to make this very thin sample to contract on one surface, but on the other surface, it expand. So in this way, it's very easy to bend. You can easily get the bending deformation. And then it depends on how you cut the sample out from the sheet. If you cut it along with the orientation, so you just get a bending. If you cut it with some angle, you end up with twisting, either left hand or right hand. So this is the trick we usually use to make the sample to get different types of deformation. And so about the material, there are so many great scientists contribute to this field. For example, Mark Warner, Ikeda, Albert Shanning, Yang Hong, and Zhao Yue, so many names. But if you are not in this field, and it's not easy to notice the names, so it's better to start with some most important ones. The first one is Professor Binkerman, because my professor told me he is the first scientist to synthesize the liquid crystal elastomer in 1980s or 1990s. I don't know the exact date. At that time, they used two-step cross-linking process. So you need to provide some part and stretch it, and then cross-link the rest of the sample. And the second one is Professor Broer from Eindhoven. So his group invents something acrylic with acrylic bond. So you can easily infiltrate the liquid crystal into a cell and use only one step polarization to get the sample, to polarize the sample. So the method provided from his group is the method I used during my entire PhD and also my postdoc. The third one is Tim White. He's the next speaker. He his group published a paper in 2012, I guess, in Science. It's about the chain extension reaction. So after this, chain extension is something you can still use one-step polarization, can combine both advantage from the previous two synthesis methods. And nowadays, in my group, all the members are using chain extension reaction to make the sample. Okay, so these are great contributor to this field and what the material can do. So I checked the topic of this summer school, and there are 6 topics. So first one is piezo. Of course, we are not going to compete with them, right? It's another material, another property. And then the second topic is light activate. Of course, the liquid crystal elastomer can change color, can change shape. And third one is fabrication. Yes, we can make it microfabrication, make microscopically, or nanoscopic is pretty difficult because the material is so soft, but we can use the material as the deforming substrate and fabricate some nanoparticles, some nano pattern by using the standard lithography. And the fourth one is printing. Yes, 3D or 4D printing in liquid crystal elastomer is a quite hot topic these days. And the fifth is characterization, of course. Every material can be characterized. And the last one, application, I think yes, because tomorrow, Yang Nagawar, I think he will tell you some nice application of his colloidal polymers. So it seems liquid crystal elastomer can just do everything. So in the following, I will choose one application which is the most useless because it's so interesting, and I believe the most interesting thing is always not so useful. It's about self-oscillation. The first self-oscillation result observed in liquid crystal elastomer, I think it's found by Tim White. It's a paper published in Soft Matter in 2008. And at that time, I was very young, very naive, and I don't understand the process. And after 10 years, no, more than 10 years, and now I think I can understand it. And now, and I will explain to you in the physicist way. And of course, for the chemist, they have other more complicated explanation. So suppose there is the sample. There's a strip, it can bend because there's a light. The light can excite the sample, can heat up the sample or whatever. Just under the light illumination, the strip will bend. Okay, so there's a light absorbing area. Now it's strict, so it's very big. Once it bends down, it will just, the absorbing area just decrease. It's some kind of, it try to block itself from the beam. It try to shadow itself from the beam, something like this. So what happened here is, if we describe this process by drawing the figure, we know the deformation of the material and energy it absorbed by the material. For sure, more energy it absorbs, more deformation it will happen in the material. But this geometry, this shell shadowing geometry, it will give the result that just more deformation, it try to reduce the absorption area, it try to block the beam to reduce the light absorption. It's opposite. So you may guess there should be a position very good at balance or equilibrium position. Not maybe half of the beam is sitting at the material and half of the beam is going through. So I prepare a video and a question for you to guess. Usually I will ask the student and they can raise their hand, but I cannot see them, or they can type in the chat box, but I cannot see the chat box. So I will answer my question by myself. The question is like this. Suppose there is a laser beam shooting to a material on the bottom. So the material will just bend over. So finally, it will stop. It will stop at position A above the laser beam, or C below the laser beam, or it will stop more or less exactly at the laser beam. So so if this is a question, I would like to ask you to guess, and I provide 4 answers. A, B, C position, and D is none of them. So of course, the answer is none of them. I'll show the video and to prove that I'm not cheating. So it will not stop. So this is a self-oscillation, and the reason for it is the equilibrium position is so unstable, and this is because of the delay of the material. It doesn't like to stop at the equilibrium position, so you just keep moving around this equilibrium position. So what is next slide? Okay, so what you see here is bending. You are using bending deformation to obtain the self-oscillation under the constant light beam excitation. If you know the trick, you can tune the deformation mode by changing it from bending, contracting, and the twisting. There should be a movie, twisting. And I believe self-oscillation is everywhere, like the waving of the leaf. You can observe some certain frequency, but the wind definitely doesn't have such frequency. And if you cook on the stove, you spare some liquid. And sometimes you find that it is oscillate. There should be some feedback. It's not so easy, this process, and I don't know how to explain, but there should be some feedback. That's what I believe. But there's one thing very important, is that this kind of oscillation, if you want to have more function, they should be non-reciprocal. It's like something like ciliary movement. If reciprocal movement, it doesn't help them to swim in the microscale. So non-reciprocal motion, especially in the self-oscillation, is important. So non-reciprocal means if you project the trajectory of the structure on the plane and the stroke area is not 0, and this means non-reciprocal. A few years ago, Professor Bohr's group, they published a paper and they used this kind of non-reciprocal, actually is a wavy-like motion, and obtain a centimeter scale walker, and it automatically walk on the surface by illuminating the light beam from the side. And I think this result is very cool, and it's published in Nature and inspires us a lot. And then I have done one of the coolest thing in my life, which is I somehow reproduce their result in a walker to walk on a human hair. This is the hair for my student, a summer student. And what we did is we drip 2 holes on the strip and shoot a laser beam below and self-oscillate. And it can walk on a human hair. So the walking direction is determined because it keep scratching, keep expanding, contracting the body, it keeps scratching on the hair surface. And on our hair, there's a microstructure, there's some scale to provide some friction bias. So it's easy to walk toward one direction than the other. Yes, and I finished the self-oscillation, and the next topic is flying. We want to make something to fly. Originally, we want to make something oscillate and fly. I think Team Y has also thought about this because he's from the Air Force. So the idea was there's three flying models in nature. We have the passive one, dispersal, gliding, and the active one, which is humming. Since the humming is so difficult to achieve, I just simply give up. And gliding is also difficult because our lab is very small, so it's easily can go to my laboring lab to make some trouble. So we start from this dandelion. So what happened in the seed of dandelion is so light and it can disperse. If there's a wind, it can fly to the sky easily. And so if there's a wind coming from the below, so what happened is on the top of the structure, it forms some vortex pattern. And so how to detect it? If you cut the vortex pattern into the cross section, what you observe is two ring pattern. So we try to see it by our setup, and this is a natural dandelion, and it forms a vortex pattern, and this is called detached separate vortex ring. And so I skipped so how to observe it. We need some particle in the air. I skipped the explanation of it. We want to make an artificial dandelion. So first we try to use liquid crystal elastomer to make the structure. It doesn't work because it's too heavy. And second step, we try to just take out one piece from nature and put some material on top. It doesn't work either because it's still too heavy. So the solution for it is to hire a brilliant student to work on this project because after getting older and older, I realized my lab skill is much worse than the student. So this is one of the greatest things we want to know in the lab. So what he did was, this is the top view of a seed of dandelion, and we found something, the textile fabric, some very thin fiber. You can cut it, and Jianfeng just stick 50 pieces on a piece of the liquid crystal elastomer film. And well, it formed the right side, the right one it formed more or less the same vortex pattern as the natural one. But the good thing is that artificial structure is so fancy that we can change the geometry. We can bend the elastomer. So we can change the angle if we shine the laser, not laser, LED actually. We can shine some light on it to bend the angle of the structure. And this will change the vortex pattern. So if it's flat, the vortex is good, and the air leaving force is huge. But if you bend the structure, the vortex will distort, and the force will reduce. Guess some of you may not satisfied with my result. Maybe you expect to see something really flying, like how to flapping the wing, like the humming robot. So there's one possibility that maybe you can do it by yourself. So there's a project supported by Academy of Finland, and we have one position open next year. If you feel interest on this topic,